Okay, good afternoon and welcome back to most of you, and welcome to the first lecture on the course on numerical hydrodynamics. It's a great pleasure to welcome Professor Ian Hawke from the University of Southampton. Professor Hawke is an expert on numerical simulations of neutron stars and the mathematical and computational aspects of fluids in general relativity. He's a key developer of some of the most important tools in numerical relativity and hydrodynamics, including the cactus code, the whiskey code, the carpet mesh refinement code, all part of the Einstein toolkit. Professor Hawke did his PhD from Cambridge and then was a postdoctoral scholar at the Albert Einstein Institute before joining the faculty of Southampton in 2005, where he's currently an associate professor and the co-director of the Center for Doctoral Training, the Next Generation Computational Modeling, which is funded by the EPSRC. So without any further delay, let me ask Professor Hawke to give the first lecture.
Right, thank you very much. And thank you all for attending and giving me your attention for the first of three parts of a description of what we need to do numerical simulations of neutron star mergers, the keys for general relativistic numerical hydrodynamics. So the links at the bottom of this first slide will take you to the slides themselves. They are browser capable. So if you open one of these slides in a browser and press S, then the speaker notes will appear. That will give you a rough idea of what I was intending to say before I went off at random tangents. The additional material at the bottom is associated with the exercises for this course, and I'll refer through the lectures to particular exercises that I think are relevant for what we're seeing. So, moving on to the first slide. For many of us studying numerical relativity and relativistic hydrodynamics, our motivation is gravitational waves. The goal was to observe these gravitational waves and use them to tell us about gravity, about relativity, about the physics of extreme objects. And with the detection of black hole mergers in 2015 and then neutron star mergers in 2017, that goal is now a reality. And the figure that we have here is the famous gravitational wave spectrogram from the detection of GW 170817, our 1 kilonova detection so far. And in particular, you can see through the Livingston signal, the high frequency gravitational waves. So now that our goal is actually a reality, the object of what we're trying to do is to squeeze the maximum possible information from observations of these extreme events. And to do this, we want both detector upgrades, but we also want better modeling of what's actually going on. So full quantitative modeling of neutron star mergers needs numerical simulation. And we'll see why these incredibly messy events rely on large-scale computer simulations shortly. So the focus of these lectures is going to be on the steps required to do this quantitative numerical modeling, and also to get some idea of what the limitations of that modeling is going to be. So our first goal in numerical modeling is to predict as closely as we can exactly this figure that we see on this slide, to predict the gravitational wave signal seen here, a chirp lasting seconds with frequencies in the hundreds to thousands of hertz. So in particular, in the LIGO-Livingston signal, we can see it's lasting roughly 20 seconds. It's moving from 50 odd hertz up to 500 in the range that they've limited to. But we generally expect that the signal will top out at a few thousand hertz. Right. So the objects that we're trying to model, the objects that were seen in GW 170817 are neutron stars, and that means they're incredibly compact. So this single observation through GW 170817 has matched well our existing theoretical expectations and our observations in other bands, particularly electromagnetism, that have already given us information about neutron stars. So in particular, we expect neutron stars to be between 1 and 2 solar masses. And the observations in GW 1708-17 were pretty much consistent with the canonical 1.4 solar mass result. The information that we've struggled in the past to get from the electromagnetic spectrum was information about the radius of a neutron star. Now, there's some information now from the recent NICER observations, but the information that came out through the gravitational wave observations was pretty consistent with the theoretical predictions of roughly between 10 and 15 kilometers. So for this one particular event, it seems that the neutron star radii was 11 plus minus 1 kilometers. So you can imagine how compact this makes the object, taking something the size of our sun and squashing it into the size of a reasonable sized city. However, there's plenty of additional information that we're going to need in order to do the modeling, more than just the mass and radius of the object. So in particular, we need information on how the matter reacts to being pushed around, to being squashed or squeezed by the gravitational field and the tidal distortion from its companion. So this is typically measured through the tidal compressibility. That essentially says how the neutron star is going to deform under the influence of its companion. And unfortunately, from just one single observation, we've got very weak constraints on this particular property of the matter. So we usually encode the information about how the matter reacts under pressure, under stresses and under strains in a single function called the equation of state. This is going to be used in our theoretical and numerical models in order to see how the neutron star reacts. Something we currently don't know well, and it's something that we want to predict and constrain from the observations, and the numerical simulations are going to be central to doing this. Right, before we go any further, we need to consider information about what resources we have available to us and what we need to do. So we want to do numerical simulations or evolutions involving neutron stars, and a neutron star contains roughly the same amount of matter as our sun. And the canonical number is that our sun contains roughly 10 to the 57 to 10 to the 60 atoms. So let's call it, for round number purposes, 10 to the 60 elementary particles. So to do a practical numerical simulation, it used to be that numerical simulations meant somebody sitting down and writing out lots of numbers by pen and paper, but now it practically means using a computer. And the image on the top left is the current fastest publicly available supercomputer in the world, Summit. And that can do about 10 to the 18 floating point operations per second. And the total world computing power is uncertain, but it's probably not above 10 to the 25 floating point operations. So even if neutron star mergers were the sole purpose of computers on this planet, you could see it's not going to be practical to do an evolution of every single particle inside a neutron star merger. It would simply take longer than any useful timescale. The old joke is that the useful timescales in astrophysics is essentially 3 years, because that's the length of a meaningful PhD project or research grant. It's going to take many, many orders of magnitude more than that to simulate every single particle in a star. So if we can't simulate each individual particle, what's the other extreme? Well, the other extreme is that we're going to average over the particles in some way. And the hydrodynamics approximation, the focus of what we're doing here, is to average over every single one of those 10 to the 60 particles. So the left-hand image is the sketch of how this works. Our macro scale problem, that is the thing that we're actually going to look at, is the star, the big round blob on the right-hand side. The mesoscale approximation, that's the sort of intermediate level where we're going to do our theoretical averaging calculation, that contains a fluid element, and that's the thing in the top left. Now, what's really happening, the physics as we sort of consider it at the ab initio level, is that we've got a bunch of things occurring at the micro scale, individual atoms or elementary particles. And there's a very large number of those, not 10 to the 60, but a reasonable number within every single fluid element. So what we want to do is to average over the micro scale to get rid of these, say, 10 to the 10 or 10 to the 20 atoms or elementary particles within each fluid element, to produce a much more simplified description at the intermediate or mesoscale that we can then treat as a more simplified or field theoretic description at the macro level, at the size of the star. And the way we do that is illustrated in the image on the right. So our micro level problem is all the different particles with all their different properties, here illustrated by using different colors. Now they're all moving in roughly the same direction as seen by an appropriate observer. So what we do in the averaging process is we take all of the particles within a single fluid element and we average over their mass, we average over their other properties like temperatures and so on and so forth. And in particular, we average over their velocities. This gives us a single fluid element velocity and a single set of properties for the fluid element, such as the number density of the particles. So the fluid element description depends on the number densities, that is the number of particles within the fluid element divided by its representative volume, and also the velocity of this fluid element. There will also be additional properties of the fluid element that come out from the averaging process, like the internal energies or temperatures or entropies. So this averaging process gives us a small set of differential equations to solve. With some standard approximations, so the standard hydrodynamic approximation, it is going to reduce down to 5 partial differential equations. These 5 PDEs have to be evolved on top of those describing the evolution of the spacetime. We'll come back to that in a second. So this makes the numerical simulation practical by converting an elementary particle problem into a field theory problem. Every single point in space and time is now represented by the fields that are describing the spacetime, such as the metric, and the fields that are describing the fluid, such as the velocity. However, it's thrown away and compressed a lot of the underlying physics. Now, this means there is a crucial difference of principle and of scale between vacuum relativity and relativistic hydrodynamics. So vacuum relativity, Einstein's field equations, is a theory of principle. Once you've described the manifold structure, we believe that it holds at every single scale. Now, if you're a quantum field theory person, you might immediately complain that actually there are length scales on which you expect the equations of general relativity to break down, but that's at the Planck length, which is practically irrelevant for all of our purposes. When we're talking about relativistic hydrodynamics, we've averaged over fluid elements. We've made assumptions about the mean free path of the interactions between these particles. We've made assumptions about the length scales on interactions between particles and more extended fields, like electromagnetic fields. So that means our models will break down on certain scales. So we have to keep in mind that as computer power and numerical accuracy increases, our results might start hitting those limitations. We might start to get to the point where we need to add more complex modeling simply because our numerical simulations have got to the limits where our physical model actually is breaking down. So let's talk about what we need in order to model an inspiral. And in the hydrodynamics approximation, we're in the simple picture that we have here on the right-hand side of the slide. So the neutron star is being modeled as a fluid ball with no additional composition, except possibly for a bulk internal magnetic field, which we'll talk about later on. So this is our starting point for a simulation. We are going to solve a set of partial differential equations describing the space-time and describing the matter. We're going to do that within a domain. So this domain is essentially going to be a box. We'll think of it as a cube that we'll put around the neutron stars. And within this box, we're going to solve the PDEs in order to evolve the space-time and the matter, and in order to extract observational signatures like gravitational waves, neutrinos, emissions in the electromagnetic spectrum. And the way that we do this, the way that we do pretty much all numerical simulations, is to split that box into smaller pieces, grid cells or points or elements, and so on and so forth. And within each one of those smaller pieces, we will replace the partial differential equation with a discrete approximation that can be solved on a computer. The smaller those small pieces, the more accurate the solution, but the more computer time and memory we're going to need. So what we want to do is to use the least amount of computer time and memory so we can cover more of parameter space, but it needs to reach some minimum level in order that we can accurately describe the physics. So what are our minimum requirements? Well, the first one comes from the gravitational waves. If we think back to the gravitational waves detected in GW 170817, the crucial feature that we need to know is what was the frequency of those detected waves. And the detected waves were in the range of hundreds to thousands of hertz. So as the waves travel at the speed of light, we can convert those frequencies to a wavelength by essentially doing speed of light divided by frequency. And that suggests that the gravitational wavelengths that we're going to be interested in here are around 10 to the 6 meters. Now, if you're trying to do a even theoretical description of a wave, but certainly a numerical description of a wave, then you need to be able to measure at least one wavelength within the box in order to get the signal captured accurately. In fact, you ideally want to put many wavelengths inside the box, let's say at least 10. This is not just so that you can get a clean and accurate measurement, but it's also to ensure that the wave is propagated far enough from the source, that is the merging neutron stars, that it's not contaminated by being deep in the strong field regime, but also that it's far enough away from the artificial boundaries of the box, which may interfere with any wave extraction that we do. So this means that our grid size is going to be at least 10 to the 7 meters to a side. Okay, so now let's think about the size of the grid cells. Those are the small boxes that we're going to split our domain into. Now, we've averaged over all our particle motion to produce a hydrodynamic model. So in a fluid model like this, just as in a space-time evolution, information propagates along waves, and these waves travel at finite speed. So the numerical accuracy depends on how accurately you can capture the amplitude of this information propagating with each speed, but also how accurately you capture the phase, how accurately you get the speed of these waves. And this is qualitatively different, as we'll see later, from the space-time. With the space-time, all the physical information propagates at the speed of light. In the hydrodynamic case, the physical information propagates at speeds that depends on the data itself. So this can be more complicated to capture. Now, there's a back of the envelope calculation, which is roughly in the middle of the exercise sheet, on phase accuracy for numerical simulations. And it depends essentially on the size of the object, the size of the wave. So when you've got a neutron star with a diameter of around 25 kilometers, your basic wave is going to have a wavelength of the order of 25 kilometers. And it also depends on how fast something is oscillating. There we can look up the frequencies of standard waves on isolated neutron stars to see that over the last roughly 10 orbits, a neutron star will undergo roughly 30 oscillations in its fundamental mode. So we can then look at what it takes to capture to around, say, 1% accuracy, the information that's propagated around and about the neutron star as part of that fundamental wave oscillation. And that says if you want to get around 1% accuracy, you need a grid cell size of around 100 meters. So we've got a box which is 10 to the 7 meters to a side. We've got grid cells that are going to be around 10 to the 2 meters. That means in 3 spatial dimensions, we're going to have 10 to the 15 grid cells inside our box. So that's a fairly large number. But the number of grid cells is not our only restriction. When we evolve forward in a numerical simulation, what we have to do is to take a single time step for each one of those cells independently. Once we've taken a single time step for all of the cells, then we have enough information to take another time step, and so on and so forth. Now, the problem is that we need to consider how large those time steps can be. And there is a stability condition that restricts how large that time step can be. We can think about this in relativistic terms. So if we think about a grid cell at some point in space and time, we think about its past domain of dependence, the light cone that is essentially emitted by photons traveling backwards in time. Now, every single grid cell that touches on that past domain of dependence could, in principle, have a physical impact on the value of the quantity at that future time. So that means that in order to calculate the quantity at the future time, we need to have considered the impact of every single grid cell within that past domain of dependence. And that means that the maximum stable time step is given roughly by the grid cell size divided by the speed of light. So given that our grid cell size is around 100 meters, this means our time step size has to be around 10 to the minus 6 seconds. Now, how long are we actually going to evolve for? To do the actual merger simulation, the last 10 orbits, that takes some numbers of milliseconds. But more importantly, what we want is a self-consistent model of the entire kilonova process. So that's the orbital inspiral, merger, collapse to black hole, formation of remnant disk around it, evolution of that disk, collapse of that matter onto the black hole, which is then expelled. And for GW 170817, the GRB flash appeared a couple of seconds after the peak in the gravitational wave inspiral. So we're going to be hoping to do a numerical simulation that lasts, say, 2 to 5 seconds. Now, this is pretty much impractical because it's going to involve 10 to the 6 to 10 to the 7 time steps, which with 10 to the 15 cells means that we need to look at 10 to the 20 to 10 to the 22 cell updates. So no current simulation evolves for a full second. Most current simulations will evolve for 10 to hundreds of milliseconds, but do typically use resolutions around 100 meters. So we need to consider what physics we can capture within a model on those scales, what behavior we should expect, and how we can simulate that numerically. So just to re-emphasize that point, GW 170817 was a multi-messenger event. So far I've focused on the inspiral phase and on the gravitational waves, but a lot of the interesting information, as I'm sure you'll see later in the school, came from the kilonova observed through electromagnetic signals in gamma rays all the way down to radio. So our expectation is that with current gravitational wave detectors, we're only going to get information from the inspiral itself. Even the most extreme event will not give us something we can see post-merger. So for detailed numerical models of the matter, as well as solving space-time, we're going to need to predict the electromagnetic and neutrino emission from the messy post-merger situation. So to consider what physics is required, I'm going to quickly show this movie, which comes from Bruno Giacomazzo's group. Should it play? So this is a simulation using a single perfect fluid with the magnetic field. If I stop it at this point, we can discuss what it's actually covering. So it's ignoring dissipation, viscosity, heat transport, magnetic resistivity, superconductivity, superfluidity, the elastic crust of the neutron star, radiation transport, modified theories of gravity. Okay, there's huge amounts of physics that we could in principle add, but this is still a huge calculation, even just, and I say that word advisedly, evolving full general relativity, modeling the star as a hot fluid with an ideal electromagnetic field. So the stars are initially inspiraling due to the emission of gravitational waves, as you would expect. And around 15 milliseconds after the start of the simulation, we get the merger of the neutron stars. And at this point, things get really messy. So when the stars smash together in this fashion, there's a shock that's propagating through the merged object. And if you focus on the central line there, you can just about see the way that the density, which is being plotted here, is jumping. At the same time, the stars, having smashed together at an angle, the material is slipping past each other. So each companion neutron star is trying to slide past the other. And this winds up the total magnetic field. There's a dynamo effect that hugely increases the magnetic field at this point. So the remnant is going to try and settle down with a lot of matter ejected, but fairly low density matter. But at around 30 milliseconds, so at this point, we can see that the central object has been unable to support itself against the gravitational field. So there's pressure support from the hydrodynamics, from the magnetic field that's been strongly wound up in the center, and effective pressure support from the rotation. But this isn't enough to keep this merged remnant from collapsing to a black hole. And shortly after the collapse, we see that large chunks of the matter is directly accreted onto the black hole. But there is still a fair amount of matter in the exterior, and it's this remnant torus that we expect in the long run to eventually lose its own pressure support, collapse onto the black hole, and that's when the kilonova occurs. So we see that in order to do the numerical modeling, even in this fundamental base level simulation, we need to model the fluid interior and the vacuum exterior. We need to model the shock as the stars smash together. We need to model the resulting jumps in temperature. We need to model the small scale structure in the interior as the magnetic fields wind up, because that's going to form the precursor to the jet. And we need to do this on top of evolving the space-time, tracking any black holes that might appear. So that is the first section of the talk, laying out the fundamentals of what we are aiming to complete. So while you take a look at how far we've come in 20 years from this first simulation by Shibata and Iyer of a binary neutron star merger in relativity, have a stretch, add any questions about this section to the chat, and we'll be back in a minute or so to answer those questions.
Thank you. There is a question on the chat box.
Okay. So the question is, can all these not be scaled by the speed of light also to reduce the computational costs? So I'm guessing this question is linked to the dimensional scaling that I was talking about the sizes of the grids and everything else. And the answer is essentially no. So in everything that I'm doing, sorry, in everything that I'm going to show in the next couple of days, I'm going to be using units where C is equal to 1. Of course, when I was talking explicitly in terms of meters, I've not done that scaling. However, unlike in the black hole case, where in vacuum everything is essentially dimensionless, in this case, the hydrodynamics itself sets a fundamental scale. So if you try to rescale any of the coordinates, what that is going to do is going to feed back into, for example, the propagation speeds inside the matter or scalings inside the grid length. So unfortunately, any gauge scalings is not going to have any impact on the computational costs. So the second question says that the final neutron star mass and the equation of state can vary. So how to take different situations into consideration. And unfortunately, there is no shortcut here that we know of right now. In essence, what you're describing is a parameter survey. And this is sometimes discussed, particularly in the numerical modeling literature, sorry, under the term of uncertainty quantification. So we don't know exactly what the masses were that went in to the neutron stars that started off. We don't know what the equation of state is. So these are the uncertain parameters. Because of the complexity of the models, the only way that we know of to do this is to fix the neutron star mass and equation of state to some number, run the simulation, get the outputs, and then compare to observations. And then we go back to the start, change our neutron star mass and our equation of state, and evolve again. And then we keep doing that until we've got some idea of how the outputs, the observables from the numerical simulation, are linked to the inputs. Unfortunately, this is an extremely expensive approach, and there's no royal road at present. There are certain approaches that people take. If you look at papers related to what's called the I love Q relations, then certain bulk properties of the inspiral can be linked to the moment of inertia of the stars, for example. And the papers of Andy Bauschwein go into some detail of producing a reduced order model from this. But because of the shock physics through the merger, it is pretty difficult, if not impossible, to directly produce some reduced model that we can trust. And certainly there's nothing that can easily be done right now other than throwing computer power at it. Right. If there's one more question. So how important are factors like superfluidity, etc., that we mentioned in gravitational waveforms in particular and of the jet physics? So I'll come back and talk about this in the third lecture specifically, but the shortcut answer is on the gravitational waves, almost zero, which is to say we won't see any difference through LIGO. We might see some difference in third generation detectors like ET. On the post-merger physics, the impact could be very large, but this is very uncertain. It depends strongly on how the temperature jump propagates through the star, and also on what temperatures are required to stop these effects coming in. But yes, Wednesday's lecture will talk about that in some more detail. Okay, so thank you for those questions. There'll be another break for questions in probably about 30 minutes or so. But for now, I'm going to move on to the next section, where we start getting deeper into how we convert the general picture that we've had so far into the numerical simulations that we're going to do. In particular, the theory behind the numerical simulations is where we're going to start. So we now know the outlines of the problem. We want a model of the matter. We're going to couple that to general relativity, and we want to be able to write this as a set of partial differential equations. So we're going to want to encode the detailed physics we're interested in, the level we can simulate with our given resources. And there's a lot of physics input that goes into that. But in addition to what we need to say specific to our relativistic matter model, there are a lot of things that we can say in the general case for any given matter model. And the reason for that is because Einstein's field equations automatically impose stress energy conservation. Divergence of TAB is equal to 0. So this is going to give us 4 equations of motion. Look at the free index B on the stress energy conservation equation. However, we don't want to write this using covariant derivatives, because when we do a numerical simulation, we need to convert everything into coordinate-based partial derivatives. So the most generally useful way to work is to pick a tetrad. This is a set of 4 vectors. One of those vectors is going to be time-like, the other 3 are going to be space-like. Usually they're orthonormal, and they're usually associated with the coordinates in numerical simulations. So the reason that we do that is that when we pick any one of these tetrad vectors and we contract it with the stress energy tensor, we end up with a vector. And the covariant derivative of a vector, or the covariant divergence of a vector, I should say, can be written as the partial divergence of that same vector. So by contracting the stress energy tensor with the tetrad vector, we can write the covariant derivative of it as this total partial divergence. We can also expand it using stress energy conservation to see that it's equal to the stress energy tensor contracted with the covariant derivative of the tetrad vector. So why is this useful? Well, the term on the right-hand side that involves the covariant derivative of the tetrad vector, that's known, completely known. We're only taking derivatives of a known tetrad vector, which is linked to our coordinates. So it's going to depend on derivatives of the space-time quantities. By pulling up the metric determinant from this term here, and by writing out the total for divergence in a sort of 3+1 split fashion, so separating out the time from the space partial derivative, we end up with the partial derivative with respect to time of some quantity plus the total 3 divergence of some flux quantity is equal to a source term. And this is generically known as a balance law form. In this case, we're going to get our general quantities from, well, the conserved quantities, the Q's, come from the time-like component of the tetrad vector contracted in with the stress energy tensor, whereas the fluxes come from the spatial component of the tetrad vector contracted with the stress energy tensor. Right. Now, it's fairly useful to look at this equation in simplified situations. For example, if we restricted to Minkowski spacetime in Cartesian coordinates, then the covariant derivatives of the tetrad vector would vanish and the source terms would vanish. This would be a conservation law. So this is expressing conservation of total energy momentum through 4 equations of motion. However, we shouldn't get too carried away with this interpretation, because even in flat space, Minkowski spacetime, if we chose spherical coordinates, then the covariant derivative of the tetrad vector would give us non-trivial effects. We'd have geometric source terms. So these source terms don't necessarily express the exchange of energy and momentum between the space-time and the matter. They encode the gravity, but they also encode the general geometric effects. So these give us 4 equations of motion. As I discussed earlier, we're expecting for a fluid that will need 5 equations of motion. And as soon as we include more fields, electromagnetism, neutrino transport, and so on and so forth, then there will be more fields that we're actually going to need to consider. So in particular, we're going to need to come up with more equations of motion. Okay, so Anchor has said he could not understand how the flux term comes in the balance law equation. So in particular, if we look at this particular, so let me look at this term here. So the flux term comes from setting the A term, so the A index equal to J. We are summing over the B terms. The J label here corresponds to a label on the tetrad. So this is going to be either one of the time-like or space-like vectors, but it may still have spatial indices. So the flux term, so the jth component of the flux term, sorry, the ith component of the flux term is essentially going to be EBJ TIB multiplied by a square root minus G. Okay. So on to the next stage. The fact that we generically have balance laws or conservation laws immediately gives us important information about the way that things are going to evolve. And to see this, we need to discuss characteristics, and we need to discuss the way that these equations appear to be solved. So here are 2 of the simplest conservation laws. The first one is the advection equation. So we've restricted to 1 spatial dimension. The flux function is now V times Q, where V is some constant number. And the advection equation can be directly solved. So the solution, given some nice smooth initial data, as we have here in the top right, the solution propagates to the right with speed v. So we can see the form of this sine-like function is unchanged. It's just propagated across to the right. And by interpreting that in a space-time diagram, that's what this picture here is, the solution is constant on straight lines in space-time. So these characteristic curves are lines on which the solution is unchanged, and they have slope v corresponding to the advection speed v. So in order to solve the problem, we find some point at future time, we find the characteristic curve that goes through that point, and we trace it back to our initial data. Having located the initial data, we can then find what the value was at that point, and that tells us what the solution is at the future time. Now, for a nonlinear problem like Berger's equation, where the flux function is quadratic, it's a half q squared, we cannot do that. It does not have a generic solution. But locally, provided the solution is differentiable, we can rewrite this by taking the derivative of the flux function. So Berger's equation can be written as dtq plus q dxq equals 0, as long as q is differentiable. And in fact, generically, if that flux function was just f of q, then this would be written dtq plus df dq times dxq equals 0. So that means that by comparing to the advection equation, we can say that locally the information will propagate to the right with speed q for Berger's equation, or in general, speed df dq. So what does this mean if we look at the same initial data for Berger's equation? Well, with this sine-like solution, the region on the left, the data is positive, so it's going to propagate to the right. The region on the right, the data is negative, so it's going to propagate to the left. Also, the region at the peak, where this arrow here is, the left-hand arrow is, that is going to propagate faster than everything else. It's going to propagate faster than the information to the right of it. Equally, at the trough, indicated by the right-hand arrow, that's going to propagate left faster than everything else, particularly faster than the material to the left of it. So in a short time, we see that the material has crossed into a shock. In the space-time diagram, what we see is that along characteristic curves, the information is meant to remain constant. But at a certain finite time, the characteristic curves have crossed. So we have a multi-valued solution. The conservation law is going to fix that by picking one particular value. This characteristic breaking is a key aspect of shocks. So the key point I want to make here is not just about the existence of characteristics, but also that this is a generic feature of any conservation law. And we've seen that for a generic matter model, Einstein's equations leads to stress energy conservation, leads to balance laws, which are going to see shocks forming. So this should not be a surprise. It is something that we've seen and described in the neutron star merger process, but it is an essential thing that we need to consider, and it is the source of many of the problems with the numerical simulations that we have. So here is the first of those problems. So we saw when talking about the scalar cases, the advection equation and Berger's equation, that what we could do was trace characteristic curves, even if that was only locally, in order to find the speed of propagation of the solution. However, when you have discontinuity, what you have is that two different characteristic speeds will appear on either side of the shock. And that means that you can't do the characteristic tracing in that sense. So in the exercises, there's a brief exercise on deriving the Rankine-Hugoniot conditions, which integrate over a small space-time volume around the shock. And what they give you is the Rankine-Hugoniot relation here, telling you how fast the shock is propagating, that's Vs, in terms of the jump in the conserved quantities, Q, across the shock, and the jump in the fluxes, F, also across the shock. Now, this has to hold for any conservation law, and it tells you how fast the shock is going to propagate. Now, the issue comes when we start thinking about how important conservation law form is. So, we've already discussed Berger's equation in conservation law form, and that it can be reduced down to the what's called the strong form, the non-conservative form, dtq plus q dxq equals 0. So what I want to consider is what happens if I didn't have the conservation law form, if I derived my equations of motion from some process that gave me an equation like this in non-conservative form. So the problem is that we can write down more than one conservative form that is equivalent to the conservation law form above. So for Berger's equation, for nearly every n, so n can't be 0 or -1, the conservation law form at the bottom is equivalent, provided the solution is differentiable, to the strong form of Berger's equation. So because the equations of motion are equivalent, as long as the initial data is continuous and differentiable, and as long as the solution remains continuous and differentiable, the solutions will be identical. However, and again, this is on the exercises and should be checked, what you'll find is that the shock speeds associated with all of these different conservation laws, so for every valid n, so essentially positive real numbers, you will get different shock speeds. So as soon as discontinuity forms, as soon as we're in that messy post-merger regime, the solutions are going to be different. And that means that if we don't get the conservation law form correct, then everything after merger is going to be wrong for our numerical simulations. So the total derivative form is crucial. If we don't have the total derivative form, then the only thing we're going to be able to do is the inspiral phase. That's only true as long as shocks don't form in the inspiral phase, which is not fully guaranteed. So the standard punchline at this point is to say, you have to work with the conservation law form. This isn't strictly true. You can work with non-conservation law forms, provided you put in the information about the shock speeds by hand. So the issue that we've got here is that we haven't put in what the shock speed is, so the numerical method will implicitly do it for us. We can constrain our numerical method further to enforce that a shock propagates at a certain speed. However, this is rather complex to do. The methods for doing it are still in their infancy in the numerical analysis community, and at the moment there's very little work on this done in relativity. Right, so having talked about these general cases, we should move to talking about hydrodynamics specifically, so the Euler equations of ideal relativistic hydrodynamics. So we discussed this early on. Our total stress energy conservation is giving us 4 equations, essentially conservation of energy and conservation of momentum. When we talk about the standard ideal fluid, as we talked about in the averaging process earlier on, we find that we need more information. Our minimum information is the number density, that is the number of particles per average unit volume. And we usually, in real simulations, write this in terms of the actual rest mass density. That is, we're taking our number density and multiplying it by the average mass per particle. Then in addition to that, we need to know what direction and how fast the fluid element is propagating in. So we need the 4 velocities. So that's a unit 4 vector containing 3 pieces of information. That's typically written U. And finally, we need information about what's going on at the microscale. How much variation is there and how much impact does it have on the neighboring fluid elements? And that can be expressed as an entropy or a temperature. Mostly in our numerical simulations, we express it in terms of a specific internal energy, but any other form will work. So that's 5 independent quantities. So in addition to our 4 partial differential equations that we get from a generic approach, we're going to need 1 more. We're going to need and to put in more information. And the standard thing that we do is that we assume particles are neither created nor destroyed. So that means that the particle number flux is conserved. And in our context, that means that the total covariant divergence of the number flux, or the number density, which is n times the mass per particle, which gives us rho, multiplied by the fluid velocity, so that total divergence is going to vanish. then we can use the methods that we did when we converted stress energy conservation into a set of PDEs. This is a total divergence. So we write this as a metric weighted partial divergence. Because we haven't had to contract with a tetrad vector, this is going to remain source free. So this continuity equation, even in relativity, is source free. So the only additional step we need to take is to write down the stress energy tensor. So the stress energy tensor is going to depend on the total energy, which is essentially going to advect itself along with any flow. So that's this first term. Self energy comes from the rho piece. 1 here, well, that should be a c squared if we were keeping track of the dimensions correctly. And then there's the internal energy within the fluid element, which is rho times the specific internal energy. Now, there's also going to be forces acting on the fluid element due to shears and stresses from the neighboring fluid elements. So how much are the particles in other fluid elements banging into this fluid element or dragging the fluid element at its boundaries? Now, in the ideal case, which is what pretty much everybody is using, we throw away any shear stresses. So the only forces that we consider from neighboring fluid elements come from those that are acting purely spatially. So that is spatial with respect to the fore velocity. So this perp tensor here is GAB plus UA-UB. You may have seen a similar projector in the description of the 3+1 formalism. That projector projects normal to the observer, normal to the slices. This projector is projecting normal to the fluid fore velocity itself. So at this point, we have a complete description of the simple model, almost. We have 4 equations from the stress energy tensor and 1 equation from the continuity equation. That's 5 equations in our 5 unknowns, rho, u, and epsilon. The problem is, in order to complete our description, we talked about the forces between the neighboring fluid elements purely in terms of u, but we didn't talk about their magnitude. So the magnitude is due to the pressure. The pressure acts isotropically, so we need to relate the pressure to our other quantities. And the way we do that is through the equation of state. And you will often hear or see numerical people talking about the equation of state as if it's solely a function that tells you how to get the pressure from other quantities, like the other thermodynamic quantities. Of course, generally in a statistical physics level, the equation of state is really telling you about the energy at the micro level and how it averages to the meso level. The pressure comes about by taking appropriate derivatives of that energy. Now, before we move forward, we should talk about more complex models, purely at this existing level. So when we first constructed the hydro averaging approximation, we did this by averaging over all particles. So if a particle was an electron or a proton, we didn't care. We just treated it exactly the same. We counted them up. If one particle was 1,000,000 times more massive than another, we didn't care. We just averaged over them all. And you can easily think of situations where this is a terrible approximation. So if you're thinking about how the pressure matters, then it's clearly going to be the case that if some of the particles that you're averaging over are much more massive, then it's going to matter a lot more for the pressure contributions. That say half our particles are 10 times more massive than the rest. So the way that we deal with this is that we can keep track of the relative proportions of the different particles involved. For example, a lot of equations of state care about the lepton fraction. That is, how many of our particles within our fluid elements are leptons, like electrons. What we can do is we can introduce the particle species. So let's say the particle volume fraction or number fraction. So that would be Yx. So the electron fraction would be Ye. And then we can advect that around with the flow. So we essentially extend the continuity equation to have the flux of the leptons. And if these are going to be conserved, then they will also obey a continuity equation of this form. From that, we have an equation of motion for the particle species fraction, and that can be plugged into the equation of state in this form to give us a more complex model. Now, obviously, in general, there's going to be micro or even mesoscale reactions taking place. So we could further extend our mixture model here by replacing this continuity equation and changing the 0 on the right-hand side, saying that the particle number is conserved, to add in a creation and destruction term. When particles interact, they change from one species to another. This is straightforward enough to do numerically, but physically needs to be done with some care, because there's going to be an impact on the energy momentum. So we need to think very carefully before we do that. Okay, so somebody's dropped a question about shear stresses into the chat. I'll talk further about shear stresses in the third lecture, but I should say that the usual way that you quantify the importance of shear stresses and non-ideal effects is through, for example, the Reynolds number. And typically, for most of the matter, the Reynolds number is such that it is a reasonable approximation to neglect the shear stresses. Unfortunately, the words most of the time and most of the space are doing a lot of work there. So while there's no shortcut for seeing that they can be neglected, there are calculations that suggest it's reasonable most of the time. That's not enough for a number of people, and you will find work, for example, out of Rizzola's group from Frankfurt, or obviously Shibata and the Japanese groups that are working on quantifying how important these effects are. Okay, so moving.
Ian, there is one more question, just one bit more.
Right, sorry, I missed that question. Sorry, I'm only seeing the question about the, right, okay. By mixture models and adding source instead of 0, do you mean that we do this in case of fluids containing electrons, neutrinos, positrons? So what I'm thinking here is that particularly in high temperature regions, what you're going to get is particle interactions that can lead to, for example, Erker interactions, for example, either lead to electron-positron interactions leading to the emission of neutrinos and deposition of energy, or you can have positron-positron interactions or conversion between pretty much any sort of different sets of species. These are particularly important if you're interested in radiation transport, because a lot of the generation of radiation effects is going to be heavily linked to the evolution of the different species fractions. However, it can also be important for coupling to certain theories of electromagnetism. My feeling is at the moment the approaches that people have taken in the field are a little bit ad hoc, and that more care is going to be required, but hopefully I'll have enough time to touch on this further in the third lecture. Okay, so in order to build up some intuition before we go too much further, I'm going to look at the equations of hydrodynamics in particular limits, particularly the slow motion limit. So it's always useful to compare your equations of motion to various limits, because it gives you ways of testing and checking your numerical methods, algorithms, and codes. It makes it easier to debug. But particularly for our interests, we want to compare to the Newtonian limit, where the speed of light is very large compared to the fluid velocities, and the pressures and internal energies are small. And it's particularly useful to us to do this because, well, there's a lot of people building codes for doing hydrodynamics in the Newtonian theory. So we can pick up, steal, beg, borrow techniques and codes from academia and from industry, from the very large community that works in this area. So the Newtonian equations in 1 + 1 spatial dimension are sketched here. So the first equation is the continuity equation. We see dt rho plus dx rho v equals 0. So if we compare this to the advection equation we saw earlier, we can see the density is essentially being advected along with speed v. Of course, this is slightly more general because v is now a quantity that we are solving for. The second equation is the momentum equation. So rho v is our momentum that we're evolving forward, and we can see that's also being advected along. So we've got rho v times v is the first term, but in addition we get an interaction with the pressure. So the pressure gradient is pushing, resisting, or accelerating the fluid. And the final term is essentially the total energy. So it's linked to rho times the specific internal energy, but there's also a kinetic energy term in there. There's a 1/2 rho v squared in this capital E. But this term is also roughly advected around. But again, there's some pressure interaction there. So what we see is that there's a huge amount of advective-like behavior. Now, I've already talked about characteristics, and understanding the characteristic picture is fundamental to a lot of the numerical methods that we'll see later on, and to a lot of our numerical intuition. So investigating the characteristic speeds, that is, how quickly the information is propagating, is one of the standard bits of analysis that we would always do. So on the exercise sheet, it goes through roughly how this works, and it won't be any great surprise, given what we've been discussing, that one of the characteristic speeds is the fluid velocity v itself. And this is called the advective characteristic velocity, or the advective mode. But there are two more characteristic speeds. There's going to be one characteristic speed for each variable in the problem. So in this 1 + 1 case, we have 3 speeds. And these 2 additional speeds are the acoustic velocities. They are equally spaced in velocity space around the advective velocity, and they are v plus or minus the speed of sound. And the speed of sound depends only on thermodynamic quantities, and for simple equations of state, it's roughly given by the square root of the pressure divided by the density. So in strong shock-like behaviors, it's going to be this acoustic mode that we really care about, because that's going to jump very quickly as the pressure and the density jumps. Most of the time, information is being pushed around by the advective velocity. So for the inspiral, it's the advective velocity that's going to be doing most of the work. So now I want to go back up to relativity. So I'm going to focus on the continuity equation and the momentum equation, the first Euler equation. So in going from Newtonian theory to relativity in Minkowski space with Cartesian coordinates, so we can call it special relativity in the test fluid limit, the new features are marked in red. So inside the continuity equation, we see the appearance of the Lorentz factor. In a lot of standard SR texts, for the vacuum case, this will of course be the gamma factor. So it is given by 1 on the square root of 1 minus v squared. The point here is that rather than the gamma factor talking about the change in observers, where the observers are the lab frame and some random frame, here it's the change in observers between the lab frame and the fluid frame, given by our fluid for velocity with a spatial component v. So the Lorentz factor is of course linked to length contraction or time dilation. It tends to 1 in the slow motion limit, so we can see that as w tends to 1, we retain the Newtonian limit, and it diverges away to infinity as we approach the speed of light. So that is the term that is going to ensure that our results are below the speed of light. In the momentum equation, we see the same Lorentz contraction effects coming in through the w squared term, but we also see additional contributions through the h term, the specific enthalpy. So the specific enthalpy is 1 plus the internal energy plus the pressure divided by the density. So in the Newtonian limit, where the pressure and the specific internal energy are relatively small, 1 should again be thought of as a c squared, we're going to retain the Newtonian limit. So this is again coming in due to kinematic effects in special relativity, and it's coming in because of the mass energy equivalence in relativity, the whole E equals mc squared. So the point here is that the internal energy of the fluid can be thought of as having its own effective contribution to the mass. You get to high enough fluid velocities, the internal energy of the fluid will have a high enough contribution to the mass energy or the energy momentum in order to give us this correction to the Euler equation. So the kinematic modifications that we've seen here in going from Newtonian theory to special relativity leave the qualitative form of the conservation laws the same. So we've still got conserved quantities on the left inside the time derivative, and we've got flux terms on the right. However, they modify the quantitative details in quite some measure. So I've talked about the characteristic speeds and the speeds of propagation. These are going to change substantially when moving to relativity, but they change in ways that you would probably expect. So in particular, all our velocity is now going to be below the speed of light. The characteristic velocity for the advective mode is still given by v alone, not contracted with any Lorentz factor. The acoustic wave velocities are still either side of v. They are v plus minus cs. However, when I say plus minus here, I mean the relativistic addition formula. So the full correct version is v plus minus cs divided by 1 plus minus vcs, where of course you should add in speed of light factors there appropriately. The one other addition is that when computing the speed of sound, there's going to be a correction term that comes in from the enthalpy. So in the same way the enthalpy comes into the momentum equation here, it's also going to come into the definition of the speed of sound. So finally, we look at the equations in full general relativity, and the modifications to go from SR to GR are highlighted in this sort of yellowy gold thing. Now, at first glance, these may look absolutely horrible in comparison to the earlier equations. However, I should emphasize that the conceptual changes here are probably smaller than the jump from Newtonian to SR. So in particular, when discussing the generic conservation law form, we saw how the conversion from the covariant divergence to the partial divergence led to the appearance of terms being weighted by the metric determinants. And the metric determinants are coming in precisely inside the time derivative and also inside the flux term here. The reason why one of them is a full 4-metric determinant, the root minus g, and one of them is a spatial determinant, a root gamma, is essentially to make the units and dimensions match up. We also saw in the generic case how the source terms came in. And because the source terms don't contain any derivatives of the matter variables, I haven't bothered to expand them on this slide. So the main new conceptual difference is the fact that our lab frame may be moving with respect to our coordinates. And this comes in by the velocity terms, or some of the velocity terms, picking up a correction due to the shift vector, which in the 3+1 decomposition is describing how fast the coordinates are moving relative to our spatial slice. So the conceptual issues in the transition to GR are relatively small. The practical implementation issues are a pain. They're much more substantial. I'm not going to bother discussing the speeds of propagation because conceptually they're very similar to the SR case. The full expansion can be found in the Living Review by Font in one of the appendices. They are long and painful and not particularly intuitive. The relation between the different variables becomes much more complicated. So in Newtonian theory, we can easily see how from the conserved variables, we get back the velocities. In the relativistic cases, this becomes much more complicated as the velocities also couple through the Lorentz factor, and all of the different velocity components couple through the Lorentz factor. So this becomes steadily more complicated. Also, more care is required when dealing with the variables. We see in the full GR case, where I've gone to 3+1, that we've got covariant and contravariant components. We've got metrics appearing all over the place, so we need to be careful in how we're dealing with the various terms. Okay, one more slide before we have a break for any questions. I just wanted to rapidly touch on how we go from the equations of electromagnetism and how this impacts on our general solution. So, when talking about mixture models, I said we averaged over everything, and that includes throwing away all of the charge information. However, when we want to consider electromagnetic fields, we need to consider the charge current, which is essentially given by the difference between positively charged and negatively charged species multiplied by their individual charge. The reason for this is that the electromagnetic fields described by the Faraday tensor satisfy the Maxwell equations, which are sourced by the charge current. Now, because the Faraday tensor is antisymmetric, can be written as an antisymmetrized covariant derivative of the vector potential, that means that the Maxwell equations are only actually describing 6 independent quantities. So by projecting the Faraday tensor with respect to the fluid equation, the fluid for velocity, we can write them in terms of the electric and magnetic fields. So this gives us 6 constitutive equations which are in balanced law form. So, for example, the time derivative of the magnetic field is given by the curl, time derivative of the electric field is given by the curl of the magnetic field, and it's sourced by the current. In addition, if we minimally couple the hydrodynamics to the electromagnetic fields, which is physically well grounded, then our stress energy tensor comes from adding on the stress energy tensor of electromagnetism, which is the double trace of the Faraday tensor, appropriately scaled. However, this is, for our purposes, not actually a very useful set of equations. So we'd have our 5 equations of motion for the fluid, and we would have our 6 equations of motion for the electric and magnetic fields. But the electric and magnetic fields are varying on really short timescales. And you can intuitively see this by thinking about a magnetic field generated by a bunch of protons, big, heavy, positively charged particles moving along, and the cloud of electrons that would be small and hence spiraling around that magnetic field in very, very fast, very close, and changing very, very rapidly. So what we would usually want to do is to average over that small scale behavior. And the standard way of doing this is to take the magneto-hydrodynamics approximation. What this does is it imposes a particular form for the charge current and then takes the conductivity to infinity or the resistivity to zero. And that leads to an algebraic relation for the electric field. E is equal to V cross B. Now I'll talk about the problems with this approximation in the third lecture, but the key thing is that we've ended up in a similar situation to our earlier hydrodynamics case. We have 5 equations for the hydrodynamics, 4 generic equations from stress energy conservation, 1 from particle number conservation, and 3 describing the magnetic field. The stress energy tensor is giving us everything that we would need. So that gives us 8 PDEs, which totally describe everything that we want. However, Maxwell's equations are also imposing the no monopoles constraint, saying that the divergence of the magnetic field must vanish. And this will cause us a number of problems that we will come back to. Okay, so that was a fairly long section. So have a stretch, have a drink. I'm just going to have a deep breath, drop any questions you might have in the chat, and in the last 10 minutes or so, I'll go through a couple of final implementation questions. Okay, so I'm back. Are there any questions at this stage? Right, so I will move on to the final 10 minutes. Right, so now that we have our equations of motion, either from hydrodynamics or magnetohydrodynamics, we can in principle solve them. Before doing so, we need to check that we've got everything that we need to solve a set of PDEs. So to do that, we need the equations of motion, which we've described. We need to know what domain we're going to solve on, and we're going to think of that as a big box around the neutron stars. We need to know the boundary conditions we're going to impose. That's got a few questions attached to it. And we need to know the relationships between all of the variables involved in the problem. So first of all, let's discuss the domain. And this particular slide has a couple of tiny dots in the middle. And the reason for that is that the background to this slide is not all, but the bulk of the grid of a single simulation. And those tiny dots that I can zoom in on a bit, those are the neutron stars in the initial data. So what this slide is meant to emphasize is that the vast majority of the box that we're going to try and evolve is not going to contain matter. It's going to be orders of magnitude bigger than our neutron stars. The edges of the box are going to be far away in the vacuum. So in a sense, this makes the boundary conditions straightforward because we just set the boundaries to vacuum. However, it does make it problematic because our equations of motion, our partial differential equations for the matter, depend on conserved variables. And those conserved variables are all multiplied by the density, which means it vanishes outside the star. And that means the equations are degenerate at the surface of the neutron star when we move from the interior to the exterior. So our model is only well posed, it's only properly describing the interior of the neutron star. And we've got a transition to the exterior. A lot of people have tried to tackle this problem via a range of analytical and numerical tricks. Very few of them have managed to be successful, and so I'm just going to describe the simplest and still very widely used trick, and that's to use an artificial atmosphere. So the idea is that you replace the vacuum exterior of the neutron stars with a low density region, low density, low specific internal energy, and you leave that to evolve in principle freely. If any point in the exterior becomes problematic, for example, the density drops so low that it's 0 or even negative, or the same for the temperature or something like that, then it's reset to the atmosphere. So this is a very simple trick. It's reasonably robust, but its physical implementations are worrying. So you might worry about it interacting with the neutron star, accreting matter onto it, and that certainly happens, but the amount that happens is sufficiently small that it doesn't seem to have any impact. You might worry about it interacting with the boundaries or interacting with regions at large distances where we would extract the gravitational waves. And again, these don't seem to be serious problems. The aspects that I worry about is that it causes an interaction with the low density matter that's expelled during the merger process. And particularly, it can lead to the generation of artificially high temperatures and issues with magnetic fields that tend to propagate very rapidly in these low density regions. So when we work with MHD, particularly if we're looking at emitted electromagnetic signals, or when we're working with models where temperature is important, for example, with neutrino signals, then this could have a significant impact on the observables. So it's something that has to be improved and studied very carefully. The other aspect that I need to mention before we go too much further is about relating the different variables. And I've already touched on this. So C to P stands for conservative to primitive. So the idea is that we have primitive variables, density, temperature, velocity, and so on and so forth. These could, in principle, be observed. However, the things that we're actually evolving are the conserved variables. The fluxes that we need to evolve are typically written as functions of the conserved variables, but also the primitive variables, and maybe some auxiliary variables, such as the Lorentz factor or the enthalpy. So in the Newtonian case, there is no problem here. We take a step forward with the conserved variables, and we can algebraically and straightforwardly compute the primitive variables and any additional variables from that. In the relativistic case, even in SR, this is already highly problematic. There is a simple way of going from primitive variables to any other set of variables, but the relation that goes from the conserved back to the primitive, which we need to do in order to compute the fluxes for the next update step, cannot be written in an analytic closed form except in very special cases. Instead, what we have to do is to solve an implicit nonlinear algebraic equation. For example, we would guess what the pressure is. From the pressure and the conserved variables, we could then compute the thermodynamic quantities, the rest mass density, the specific internal energy. Then from the equation of state, we can compute a pressure. We can compare the two. If they match, then we've found an appropriate set of primitive variables. Now, this is a one-dimensional problem in the sense that we're only trying to solve for a single variable, the pressure. So we can use things like bisection and Newton-Raphson. So there's standard methods that are as fast as this can possibly be, but it's still expensive compared to the Newtonian theory. And there's always the possibility it might converge to something unphysical, a negative pressure, or that there might be multiple roots if the equation of state is particularly problematic. Now, usually when you add more physics, for example, in the Einstein-Euler-Maxwell case, the minimal coupling between the different parts of the physics in the stress energy tensor means that you can do this conversion process separately for each part of the physics. Unfortunately, that's not true in MHD. The reason it's not true in MHD is that even though the two theories are uncoupled at the energy momentum tensor level, by imposing the Ohm's law, by imposing that E equals V cross B, we've imposed a strong coupling between the two. And that means that our inversion process, our implicit equation that we have to solve, is now more than one-dimensional. Typically, people solve a two-dimensional problem. This becomes much more expensive, much less robust, and is absolutely horrible. So for real implementations using MHD, the one place where I would always say that you should not implement your own part of code is this particular conversion process from conserved to primitive variables. There's available codes based on lengthy papers by people who spend a lot of time studying them. I strongly recommend that you rely on those. Right, so we've hit our 90 minutes. So today's lecture was very much about on what our goal is, what we're trying to achieve, and the physics that we have to put in order to get the base level stuff correct. Tomorrow, I'm going to take a much deeper look into the actual numerical methods themselves, and then Wednesdays will be on more complex physics that we might put in. In the meantime, if you've got any more questions, now is the time to ask them. Thank you for your attention.
Thank you very much, Ian, for this wonderful introduction. The floor is open for questions now. All right, Ajith.
Hi, I have a more of a practical question. So when do you think during inspiral can develop shocks? In which cases? Like, I understand, but I just want to hear from you.
So you asking about shock formation before merger?
Yeah.
Right, okay. So there's a couple of things that can happen. And it depends very strongly on the physics of what's going on at the surface. So if the surface is fluid-like, then you can get what's called surface waves. So they're very similar to essentially ocean waves, and they will propagate and break in exactly the way that waves on a beach will break. So those will only have a very small impact on the dynamics of the system because they're very, very low density, but they will convert some energy from fluid to heat. So that would have an impact on the thermal signature that you would expect in the pre-merger phase. Now, surface waves are probably not going to be such an issue because our expectation is that the neutron stars that are inspiraling are old and cold. And that means that they will have a crust. That is, they'll have a region in the exterior, say the last 100 meters to 1 kilometer, sorry, that acts a bit like the Earth's crust. It's like an elastic lattice. So that's got some tension in it, which can't sort of fold over. However, there's some work done by David Sang at Bath and others suggesting that there's the possibility of a resonance between the binary companion and the crust. And this can lead to the crust shattering. And when that happens, the crust shattering can shake the magnetic field lines. This is linked to the process that's believed to cause pulsar glitches. So we know that in pulsar glitches, we see a sudden jump in the pulse rotation rate, and that's due to, it's believed, jumps in the magnetic field due to rearrangements in the crust core interface. And that shattering process will lead to shocks propagating throughout the entire neutron star. They're considerably smaller than the shocks that you would expect to occur during the merger phase itself, so they'll be fairly low temperature, but they may lead to rearrangements in the magnetic field configuration. Well, they definitely will lead to rearrangements in the magnetic field configuration, and that could have impact on the later signals. Does that cover your point?
Yeah.
Thank you.
So yeah, there are two questions, in fact, three questions in the chat box. What is a dynamo mechanism effective in the NS merger scenario?
So the idea of a dynamo is essentially if you've got a electromagnetic field that's being wound, so it's being you've got something that's conductive and you've got a moving magnetic field through it, then this will increase the strength of the magnetic field. So if we take the picture on the slide as being indicative of roughly how the neutron star is looking at the point of merger, what you're essentially seeing in this central region here is the part on the right is moving upwards and the part on the left is moving downwards. So these two parts are sliding past each other. Now, the magnetic field is typically, its strength is roughly proportional to the density. So what you're seeing is a strongly conducting magnetized fluid being pulled past a strong magnetic field on both sides. So what this is going to do is it's going to steadily wind up the magnetic field. This is perhaps easier to see with some of the images that we'll have in the second lecture. So maybe it'd be best to talk about in more detail in the second and third lectures.
So there are, yeah.
So then Surendra's question on balanced law forms, there's a contribution from the geometry, not only from the stress energy tensor. So elaborating on the geometry part, so this comes down to the advantage and disadvantage of working in general relativity, working in a manifold context, is the fact that the coordinates don't mean anything, but the coordinates must still have their impact on the differential equations themselves. So while we are completely free to choose the coordinates as we want, and we usually do that in order to make the space-time evolution practical, we lift all the gauge conditions from the vacuum simulations because they work. What we find is that, of course, the space-time itself, the space-time metric, for example, it's describing both the coordinates and the actual physics of the gravity itself. They're all entangled in a way that's not easy to separate. So when I say that the source term contains purely geometric effects as well as physical gravitational effects, in the relativistic sense, what it's doing is reflecting the fact that we can't easily disentangle those in the full metric. So it's probably best to use the idea of everything being geometry there. Okay, so the next question from Pritam about finite volume methods versus smooth particle hydrodynamics, which is preferred and why? So the bulk of the field uses finite volume and related matters, and I'll discuss this at length in tomorrow's lecture. Smooth particle hydrodynamics does underpin Andy Bouswein's simulations, which are some of the most impressive simulations of binary neutron star mergers. The advantages of smooth particle hydrodynamics are it avoids the atmosphere problem that I've discussed here, and it also makes it easier to track the ejected material. So it's stronger in that outer region. However, SPH traditionally has problems and issues with shocks, and while a lot of these have been addressed, I am personally still somewhat skeptical that SPH really works correctly in those cases. That's an opinion rather than something I could fully back up with the most recent simulations. But yes, the field is largely dominated by finite volume methods. Okay, Abhishek's question: how does one match analytical methods to numerical methods, for example, in a binary black hole simulation? Do you use the analytical results as initial data? So for binary black holes, I'm sure that Harold Pfeiffer will talk about this in more detail, but even for the initial data, while we still do a lot of analytical work to prepare the equations to solve, you still need numerical solutions for the initial data. The actual matching part is largely done from the observables. So, for example, the LIGO teams and the data analysts would take the emitted signals that we give them, and they would match those to post-Newtonian approximations, for example, and they would find a way that that smoothly connects in a way that's appropriate for the data analysis. There's a lot of work by this. There's different teams in Cardiff, teams in Spain, teams in America, working on a number of different algorithms to do this cleanly to make sure they get the results out. Okay, so the next question is, what is the typical density we assume around the neutron stars? So I'm assuming that this is linked to the atmosphere. So that varies very much depending on the numerical methods that people use. But let's remember that neutron drip density is around 2 times 10 to the 14 grams per centimeter cubed. And so the core density in the neutron star is typically around 10 to the 15. Now, we would usually have atmosphere densities that are somewhere between 8 to 12 orders of magnitude below that. So we're talking around 10 to the 7 to 10 to the 5 grams per centimeter cubed. This is still probably 5 to 10 orders of magnitude too high to be even remotely physical. There are some cases, there's work by David Radice, for example, where people have constructed algorithms that can work down to essentially arbitrarily low densities. However, the physical transition and how this works with ejector, particularly with magnetic fields, is still difficult. Linked to that is Abhishek's final question about why the surface of the neutron star is problematic. Well, there's many reasons, and many different viewpoints as to how you can see that this is a problem. So the approach that I've talked about here is that I'm thinking about solving over the entirety of the domain with a single set of partial differential equations. And the trouble is that the fluid hydrodynamic description is not valid in vacuum, because the equations of motion essentially give us a sort of 0 plus 0 equals 0 form, but we're trying to take derivatives in an appropriate fashion. So particularly across the surface of the neutron star, if we're thinking in the ideal situation where we're transitioning sharply from matter to no matter, then there's a question mathematically as to whether or not that's a sensible description. There's other problems with this that are outlined in exercises on the exercise sheet. So in particular, as you do the transition through the surface, you can find problems with the characteristic speeds. Characteristic information can degenerate. This means that numerical methods that rely on characteristic information can run into significant problems. The characteristic speeds for magnetic fields can diverge unless you are careful with dealing with your description at that point. Also, a lot of the steps that we actually take involve converting between various sets of variables, and this conversion process becomes numerically inaccurate to the point where it's actually useless as we transition towards the surface. So again, it does depend strongly on which numerical method that we use, and it can depend heavily on the details of the numerical method, but it does seem to be a generic feature that unless you're using something like a smooth particle hydrodynamic code, the surface is a serious problem. Okay, are there any more questions?
Okay, looks like not. So thank you very much for this wonderful introduction, and we look forward to hearing the next part tomorrow.
Right, so I will talk to everybody tomorrow morning.